So let's go on to the sphere now to understand the Coriolis effect. Okay, so even if you don't understand in the first go round, you just remember the things that I already said. Things get deflected to the right of the direction of motion in the northern hemisphere, to the left in the southern hemisphere, because across the equator the direction of rotation changes because the reference point from the northern pole and the southern pole are different, which means the Coriolis effect goes to zero on the equator, and it increases on the sphere with latitude, and it becomes maximum at the poles. We will see why this is so, right? So changes in the Earth's rotating velocity also is great with latitude. It's not linear. On the equator, you are basically going linearly. There is no rotating velocity, but if you step off the equator, you are going to begin to experience the impacts of rotation. And every point on Earth is going around once in 24 hours, and the equator is the largest circumference of the sphere, so any point on the equator has to cover a large distance in 24 hours, so it has to move much faster than a point at a higher latitude, right? So that gives you 1600 kilometers per hour. I think I said 1600 miles per hour in the previous podcast. Scratch that, it's 1000 miles per hour, 1600 kilometer per hour at the equator. As you go to higher latitudes, you're covering smaller distance, so you cover less distance, so the speed drops. You can see that here. On the equator, you're moving at 1600 kilometer per hour. When you reach a latitude of 33 north for New Orleans, for example, it's moving at 870 miles per hour, or 1400 kilometers per hour, so it dropped by about 200 kilometers per hour. When you reach this latitude of 60 north, it's moving at 800 kilometers per hour. So the drop is not linear. You moved 33 degrees here and 30 degrees, 27 degrees over there. You dropped only 200 kilometers per hour here, but you dropped 600 kilometers per hour over there, and by the time you reach from 60 north to the North Pole, another 30 degrees latitude movement, you obviously reach 0 kilometer because you are on the North Pole, which is not moving, right? So same thing at the southern in the southern hemisphere. So this non-linear change in velocity along the latitudes is very critical. So let's just do this by looking at the animation, which is easier to explain. How do we do it? Basically, you imagine that you are going to launch something. A missile is violence, but nonetheless, let's say we launched a rocket full of chocolates from Galapagos towards the people in New Orleans because they are feeling depressed by the hurricane that they just got hit by. What happens? The rocket full of chocolates is going to start moving north, but it's also moving east at 1600 kilometers per hour because it's launched from Earth. That's its east-west velocity. As it goes north, the Earth below it is moving slower and slower and slower because the speed is decreasing as you go north, right? Which means as the rocket is flying on in the air, by the time it reaches New Orleans, if it hasn't adjusted its eastward velocity of 1600 km per hour, is going to go much further east than New Orleans, because New Orleans is moving east only at 1400 km per hour. What happened? Relatively speaking, the direction of motion got changed just like on the merry-go-round, and the path has been deflected to the right of the direction of motion, south to north in the northern hemisphere. You're being moved east. You can understand this also by launching the chocolate rocket by, let's say, Santa Claus from the North Pole towards New Orleans, and here you are moving at 0 velocity eastward because you are coming from the North Pole. But as you go south, the Earth is moving faster and faster towards the east, and you have no eastward velocity which means you are lagging behind. You're continuously going westward relative to the surface below. So you're not going to reach New Orleans. You're going to end up somewhere far west. Right? So this is again reflected to the right of the direction of motion. You're going from north to south in the northern hemisphere, so you're going to be deflected towards the west by the Coriolis effect. Again, the speed didn't change, but the direction of motion changed. Okay? This is Coriolis effect. The tricky thing here is you have to figure out then, I said anything that moves on Earth at such large scales is going to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. So if you're happily going along a latitude circle, why would you be deflected to the right or left? We can look at it a little bit later on, but something called the centrifugal force becomes important. So since you're on a rotating framework, if the Earth suddenly stopped spinning, or if the merry-go-round stopped, for example, you would fly off at a tangent to the merry-go-round, right? So you will fly off at a tangent to Earth if the Earth stood still, right? That centrifugal force has a component towards the center of the Earth, which is in the direction of gravity. It is very tiny, so it wouldn't change the gravity by too much. But it also has a residual component that is horizontal, parallel to the surface, which is what going to make you tilt to the right in the northern hemisphere and to the left in the southern hemisphere. Okay? You can draw a circle, go off the equator, draw the centrifugal force going out of the Earth's surface tangentially, draw a line to the center of the Earth, which is the direction of gravity, and you have a component of the force left that is in the horizontal direction. That is the Coriolis effect. Okay? Should I draw it and do it? We can try, but I suggest you do it and get a good sense of why, even if you move along a constant latitude, you will still experience Coriolis if you are moving at a large scale. Everything experiences Coriolis, even the cup of kara that I'm drinking here to protect myself against COVID. It has a tiny bit of Coriolis effect. You always hear the story that the flush or the water in the toilet or the wash basin is going to go in one direction in the northern hemisphere, in the other direction in the southern hemisphere because of Coriolis. Not true, because at those small scales the Coriolis is very, very small. Plus, at those scales the frictional effects are very important. So if you rotate it in one direction, it'll go in that direction. If you rotate it in other direction, it can go in the other direction. So the initial direction you provide and the friction, etc., will become important. Coriolis effect is important when you move at planetary scales. Climate, weather, ocean motions happen at planetary scale, and that's why we get Coriolis effect to be so important at planetary scale. So I will show the animation in the next podcast, but that will kind of cement the concepts in your head. Coriolis is a very important concept, but you can see I'm saying now a lot of concepts are important, and they all are, because they will begin to add. You will have to use them together to understand